everybody. Greetings and welcome, friends. My buddies, you're my friends. We're talking about slopes, quote unquote, of parabolas. I use the word loosely. Technically, I'm referring to slopes of secant lines through points on parabolas, but whatever. So let's, yesterday we did some examples for a regularly shaped parabola. We talked about that its slopes were, had rises which were consecutive odd numbers, so it would go up 1 over 1, up 3 over 1, up 5 over 1. Today we're going to talk about some stretches and smooshes and what that does to our quote-unquote slopes. So here's, I don't like that plus sign. There we go. Here's our first example, right? So I've got f of x equals negative 2x squared plus 8x plus 10. This is a quadratic equation, function actually, better yet, because it is a does have two variables represented. So let's see, a is equal to negative 2, b is equal to 8, c is equal to 10. In the interest of time, I'm just going to give us the vertex. So the vertex is 2 comma 18. All right, so that way I can focus mostly on just the slopes. If you want to find out how to find the vertex, go check out my previous video. So there's the vertex, and let's say, well, actually, you guys could tell me maybe the y-intercept. Well, let's just do I'll skip the x-intercepts. We'll come back to that. And the y-intercept, the classic, just is whatever c is, right? So that's 10, or I could write that as the point 0 comma 10. So which way does this open? How do you know? Nope. The thing that determined our... So since negative 2 is less than 0, it opens down. And then the shape of this... Okay. Well, the absolute value of negative 2, how does that relate to 1? Is it greater than it or less than it? Greater than it, right? So absolute value negative 2 is greater than 1, so that means it is a stretch. Okay?
Sure.
So let's actually, let's see, I'm going to delete this, delete that. There we go. I'm going to get myself a grid going here. Now, I know that my vertex is at 218, so I want to be at least as high as 18, right? Yeah, I'll come back to it. And let's see, my x-intercepts I don't know. I know my y-intercept is at 10. Here, we'll do, that looks good enough. So I'll have my scale be something like that in order for my graph. So let's plot what information I do know. So the vertex is at 218, so over 2, up 18. It's opening down. I knew my y-intercept was at negative 10. Now, my axis of symmetry, I know, would be right here. Right? And so I know I could actually even mirror that point if I wanted over here. But let's talk about the slopes of this graph. So it's got a negative 2 for its a term. So the negative made it open down. The 2 means it's going to stretch twice as much as it normally did. Okay? So stretched by a factor of 2. So for my slopes, right, typically, leave some space here, it was up 1 over 1, up 3 over 1. I'm writing that weird there intentionally. And up 5 over 1, right? And in this case, what I'm going to do is I'm actually going to multiply these numerators by a. And what's a equal to in this case? Negative 2. So negative 2 times 1, negative 2 times 3, and negative 2 times 5. Okay? So what are these slopes equal to? That would be negative 2 over 1, negative 6 over 1, and negative 10 over 1. So behold...
Wait, is that why for the slopes, when it's regular, it just stays as
Sure. Perfect. Yeah, right? If a is equal to 1, then 1 times 1 is still 1, 1 times 3 is still 3. Perfect explanation. I like it. So let's see. So let's find some more points. So from my vertex, I'm going to go down 2 and over 1. And I land on a point right there. And then from that point, I would go down 6 and over 1. And hey, look at that. I land right on that point. So down 2, down 6. And from here, where would I go? Down 10 and over 1. So I actually end up landing exactly on an x-intercept, which is rare. And notice that I actually could do the over 1 backwards if I wanted. So I could go down 2 backwards 1, and I would have landed here. Or I could have mirrored that point. And then I go down 6 backwards 1, and I would land on my y-intercept. So there's some verification for us. Or I could mirror that point, right? And then down 10 over 1, and there we go. So when I graph this, I end up getting a skinnier parabola. Something like so. That's good enough. So it's stretched by a factor of 2, right? So instead of down 1 over 1, down 3 over 1, down 5 over 1, it doubled each of those rises, quote unquote. And in this case, the rises were negative, so they were falls, I guess. But that's the idea, right? And so theoretically, it looks like my x-intercepts were negative 1 and 5. So what that would be claiming is that the x-ins were negative 1, 0, and 5, 0. So that means that this actually would have been factorable if I set that equal to 0. Negative 2x squared plus 8x plus 10 equals 0. Actually, the first thing I would have done was probably divide everything through by negative 2. Yep, and then I would have gotten x with a 1, x with a 5. And it all would have worked out. How great is that? So it would have been plus 1 minus 5. And then I'd end up getting the opposites of those when I solve them. So yeah, but the main thing I want to point out today is just the slopes. So don't worry, that stuff's just side bonus. That's all taught in the previous video. So let's talk about slopes of a smoosh. I'll do the smoosh problem over on this side. Example. So let's say I want to graph, let's actually even use a different letter. Let's use w of x. So I can call this function w for waddy. Yeah, represent 1/3 x squared minus 2x plus 1. So looking at my function w, what is a, b, and c?
A is 1/3, B is -2,
And c is 1, right? So I'm actually going to have us find the vertex on this one and do all the hard work. So the practice you were hoping for is going to happen. Here we go. So the vertex, the x coordinate, I can do negative b over 2a, right? So negative of negative 2 over 2 times a third. So that's positive 2 over 2/3. I could multiply by the reciprocal. And I'm going to end up getting just plain old 3, whichever way you ended up doing that. Right? A bunch of different ways you could have kind of simplified that. So the x-coordinate of the vertex is 3. The y-coordinate, how do I find the y-coordinate? I find out, I plug in h into the function. So what is w of 3? Right? I guess I'll make that an equal sign, but now that looks weird. W of 3 would be 1/3 times 3 squared minus 2 times 3 plus 1. And 3 squared, I have to square before I multiply, right? Using PEMDAS. So 3 squared is 9. Minus 6 plus 1. 1/3 of 9. You guys, of course, know is 3, right, Aaron? Minus 6 plus 1. And 3 minus 6 is negative 3 plus 1 is 2? No, negative 2. Is So that means my vertex occurs at 3 comma negative 2 for my vertex. Aha! Vertex! Hooray! My x-intercept, I'm going to skip on this one. You would have to use the quadratic formula, though, to solve them. I don't believe they're going to be factorable. I'm pretty sure they're not. Maybe if you multiplied everybody by 3. Minus 6x plus 3. No, not factorable. So x-intercepts are going to be decimals. We'll come back to those. They're not as important in this particular problem that I'm trying to show you. Y-intercept. Oh, there's only one, so it's not plural. 1, right? It's just the old c value there, so 0, 1. So you guys should get that every time, right? Good stuff. And let's see, question, which way does this open? Because 1/3 is greater than 0. So it opens up. And how about the shape of this? Absolute value of 1/3 is less than 1. So it's a smoosh. Or you could think about it as a horizontal stretch.
I like that one better.
I'm not fat. I'm just horizontally stretched now that I'm over 30. So let's see. Open and shape. We've got,
I
so,
love how you say that, but they don't see you and you're like the skinniest person.
no, I've got a little belly. I've got a little belly. I ate a lot of chili last night, too. It was delicious. So, let's graph this. Let me get a nice little grid going here. So let's see, it opens up. What was the vertex at? 3, negative 2. Actually, you know what? I'm going to draw my own grid for this one. You know why? Here's a suggestion. Because of the fraction, use thirds. Let's see, why can't I write an R? Thirds as the y scale for our graph. And I would even use thirds if this was like a 2/3 or a 5/3 or a 7/3. So I'm mostly kind of emphasizing the denominator there when I do that. So that's what I'm going to do. So let's see. So I've got to be at 3, negative 2 and use thirds for my y scale. So here we go. So I'm going to go, so my x scale I still can count by ones. Let's see, no, maybe a little 1, 2, 3, 1, 2, 3. So here's 3. And my y scale, I said I'm counting by thirds. So that means 1, 2, 3. Every third one is a unit, right? 1, 2, 3, like that. So 1, 2, 3, negative 2. 1, 2, 3. Oh, those tick marks weren't very evenly spaced. I do have graph paper, kindly donated to us by France. Actually, I lied, the French teacher. Or Spain, I guess, because she also teaches Spanish.
That's not even the part.
Yeah, that's good enough. So let's see. My y-intercept is 3, negative 2. Okay, so right thereabouts. Actually, I don't need as dark of a point this time. So over 3, down 2. Right there. All right, so there's my vertex. And it opens up. And now let's figure out my slopes. All right, let's do our slopes here. Sloppy slopes. Sloppy slopes. Sloppy slopes. Now, A is equal to what? 1/3. So instead of 1 over 1 and 3 over 1 and 5 over 1, I'm going to multiply those numerators only, my rises, by 1/3, okay? And I'm not going to simplify these fractions intentionally because this will actually work out great. So I'm going to go up 1/3 over 1. I know that's really weird to leave it that way.
No, the next one.
This one would equal just 1. So this one's up 3/3 over 1. And that would equal 1, but I'm going to leave it like that, crazy notation. And this one's up 5/3 over 1. And yet, so I'm leaving these unsimplified. So from my vertex, I'm going to go up a third over 1. How much is a third? A third is this distance, which I conveniently am counting by. So I'm going to go up a third and over 1. And then from there, I'm going up 3/3. So here I am, right here for my height. So up 1, 2, 3, 3/3. Right? And over 1. So 3/3. And then I'll go up 5/3, I believe. So currently I'm at -2/3 for my height. And that's actually going to land me right on the 1 there, isn't it? For my height. And over 1. Right? So even though this is really weird with these fractions, it actually, as long as you chose your scale wisely, it can kind of work out really nice. So I've got a good number of points. And watch what happens when I mirror these. So let's see, this is 1 away there, so 1 away over here. This is 2 away, so 2 away over here at 1, -2/3. And this is 3 away, and what do you know? Look at where my y-intercept is. Look at where we said our y-intercept was going to be. What? Guys, it's working. That's terrible. But that's fine with me. Yeah, that's good enough. Now, I want to point out that this is a smoosh. It might not look like a smoosh. Does anyone know why? Well, it's because look at what I called 1 unit on this direction was that length, and 1 unit on this direction was less than it. So I kind of messed with my scale so the smoosh wasn't as obvious. You know what I'm going to do? I'm going to graph this electronically for us. Let's see, let's go back to our geometer's sketchpad. So I'm going to graph. And I'll do 1/3 x to the 2nd power minus 2x plus 1. And then look how awesome quick that is. And you can see that it's actually a bit of a smoosh. All right. A regularly shaped parabola would have been like x squared. Let's see, actually, let me think. What was our vertex on this one? 3, -2. Let's do x minus 3 all squared minus 2. There, that's what a regularly shaped parabola with the same vertex would have been. So you can see that it actually was smooshed. You kind of had to, if my scales were consistent, it would have been the case, right? So anyways, thanks for watching, internet friends. That's how you can deal with slopes when your A value is something other than 1. And it's kind of a cool little trick. I like it. I like it a lot. So have a great day. Bye-bye.